Hello everyone. So in today's class we will see black body. So what is the black body first of all? A perfect black body is one which absorbs all the heat radiations incident on it. So whenever we are incidenting some radiations on one body, it should absorb completely. Then that body is called black body. And always the body which is a good absorber is definitely a good radiator also. Means the body which absorbs more heat may radiate more heat also. Next one, practically no body behaves like a perfectly black body, but lamp black and platinum black are the closest approach we can say. What is this lamp black? See, shoe polish, shoe polish, it is perfectly black. So whatever amount of radiations will get incident on it, it will absorb nearest to 100%. That is what the lamp black. Okay, shoe polish or paint, something like that. One black type of color we can say, which will absorb it, which will behave as an absorbent. That is what this lamp black is. And we will use this coating in a black body. Okay, lamp black and platinum black. So next one is Ferris black body. So see, what is the Ferris black body? You can see in the diagram, this is what one spherical structure we can say, double walled sphere we can say. It has one small opening O, and through this radiations are getting incident. Here you have one notch type of thing. So on this it will get reflected, and due to this multiple reflections, the absorption percentage increases because we have coated internally with the lamp black, and that's why absorption percentage increases due to the multiple reflections. So it is a closed double walled hollow sphere having small opening O and a conical projection P opposite to the opening, which we have seen, and outer surface polished with nickel, inner with lamp black. Okay, so note down this. So as I said, after few reflections, entire radiations get absorbed. Black body could appear red, white, or any color depending on the temperature. So it is same like what you can say iron rod. It may look reddish, little bit yellowish or whitish also depending on the temperature. Same like that, black body also will appear sometimes red, white, or any color depending on the temperature. Next, black body emits and absorbs radiant energy better than bodies of lighter color. So as compared with lighter colors, this black body, either if you are considering emission or absorption, it is more only. Next, distribution curves you can see here. See here, this is intensity of radiation we can say, and this is absorb intensity, and there it is wavelength. So see, this is maximum and then it is decreasing. Here also it is decreasing. This is maximum intensity radiated for one particular wavelength, and that is what your maximum wavelength. Okay. So next topic is law of distribution of energy. It suggests you how energy is getting distributed. So see, E lambda d lambda, this is for particular wavelength. 8 pi hc by lambda power 5, 1 by e power hc by lambda kt minus 1 d lambda. If suppose the radiations are of short wavelength, if suppose radiations are of short wavelength, then lambda is very, very less than hc by kt. Yes, and that's why this a by lambda power 5 into e power minus b by lambda t into d lambda this equation reduces to this, where A and B are constants, and this equation is nothing but Wien's energy distribution law. For radiations of long wavelength, if lambda is greater than, very greater than Sc by Kt, then it reduces to E lambda d lambda 8 pi Kt by lambda power 4 into d lambda, and this is nothing but Rayleigh's energy distribution law. Okay. So next topic, that is Stephen's law. What is the Stephen's law? The emissive power of black body is proportional to the fourth power of its absolute temperature. Absolute temperature means you take it in Kelvin. The emissive power of black body is dial proportional to fourth power of absolute temperature. See here, this is emissive power and it is dial proportional to fourth power of absolute temperature. And what is this emissive power? Energy radiated per unit area per unit time is nothing but emissive power. That is what Q by T into A. Now, if I am removing this proportionality sign, I am adding one constant, that is sigma, and sigma is nothing but what? Stephen's constant. So E is equal to sigma into T power 4. As already we have discussed, this E is nothing but what? Q by T A, that is energy radiated per unit time per unit area, is equal to sigma T power 4. This Q by T is equal to this A, I am transferring this side, A sigma T power 4, and this Q by T is nothing but power, we can say. So this is dq by dt. If I am taking as a, for this Q by T I am taking dq by dt, then it is sigma A T power 4, where sigma is already we have discussed Stephen's constant, and its value is 5.67 into 10 to the power minus 8 watt meter power minus 2 Kelvin power minus 4. Okay, so let's see one note point. In this case, small e is not there, but other than black body, you will get small e, because for black body E is equal to 1. For other body, it is not equal to 1. That time, this dq by dt is equal to E into sigma A T power 4, if they have given small e value. Now, dq by dt is equal to E sigma A T power 4 minus T0 power 4. And already we know this dq is equal to what? Ms d theta, but here I am denoting with dt. So dq by dt, just divide with the dt, we can say. So dq is equal to ms dt and divide by dt. That's why dq by dt is equal to ms dt by dt. Just substitute here this value, and what we are getting, dt by dt is equal to E sigma A ms. Just to transfer this side, and you will get dt by dt is equal to E sigma A by ms T power 4 minus T0 power 4. Which is what application we can say of this Stephen's law. Okay, note down. So let's move ahead. The next topic is Kirchhoffs law. So what is this Kirchhoffs law? E lambda by A lambda is always going to constant. What is E lambda? Emissive power, and A lambda is absorptive power. So the ratio of emissive power to the absorptive power is always constant. That means E lambda is dial proportional to A lambda. Good absorbers are good emitters. Good absorbers are good emitters, means the one which absorbs better, it may emit better, or it emits better. For example, you see in deserts, days are hot and nights are cold because sand is there. This sand will absorb heat more. At the same time, during night time, it will release also more. And that's why this is what one application of Kirchhoffs law we can say. That is, in deserts, days are hot and nights are cold. Now solar constant. This is a sun whose radius is A, here it is Earth, and this B is what? Mean radius, we can say. Now this A is radius of Sun, B is mean distance between Sun and Earth. Now P is equal to dq by dt, which is equal to A sigma Ts power 4. This Ts is what? Surface temperature of Sun. Now what we have to do? We have to find the surface temperature of Sun by using this solar constant. Let's see. So now this A is there. I am replacing this A with 4 pi A square, which is nothing but surface area of Sun. And that's why I'm getting P is equal to 4 pi A square sigma as it is, Ts power 4 as it is. And this Ts already I told, what is this? Temperature of surface of Sun. Now solar constant is what? This power and this complete area of this sphere. This is P by 4 pi B square is nothing but solar constant. Now let's substitute this P value, whatever we got here in this solar constant formula. So I'm substituting here 4 pi A square divided by 4 pi A square sigma Ts power 4 divided by 4 pi B square. Then this 4 pi cancel. A by B whole square sigma Ts power 4 is what? Solar constant formula. Now we want to find surface temperature of Sun. So first note down this. So let's move ahead. So S is equal to A by B whole square sigma Ts power 4. And now we have to find surface temperature formula. So see, I'm just transferring this term here. Sigma I transferred here. S by sigma A by B whole square down. Now this S by sigma as it is, and this A by B whole square I'm writing as a B by A whole square. Okay. And then I'm taking fourth root, that is Ts is equal to S by sigma B square by A square whole power 1 by 4. And this is what your surface temperature of Sun. So P is equal to 1.5 10 to the power 11 kilometer. That is what mean distance between Sun and Earth. A is equal to 7 in 10 to the power 8 meter. That is radius of Sun. Solar constant is 1400 watt per meter square. And this Stephen constant, you know, what is that? 5.67 in 10 to the power minus 8 watt meter power minus 2 Kelvin power minus 4. So if we will calculate, or if we will substitute this value in this formula and calculate the surface temperature, we will get nearly 6000 Kelvin. Okay. Right. Let's move ahead. Now greenhouse effect is what? Some of the heat trapped by CO2, CH4, O3, CCl2, F2, etc. gases and water vapors add to heat the atmosphere, causing global warming. This is called natural greenhouse effect. So effect of global warming is what? You know already. Melting of ice caps, sea level rise, unseasonal rains, and increase in infectious diseases like dengue, fever, and all these things, malaria and all. So how we can overcome this? By planting more trees and by reducing the production of chlorofluorocarbon. Okay. So note down this. So this one already we have discussed. Global warming can be prevented by planting trees and reducing production of chlorofluorocarbon. Now next topic, that is Newton's law of cooling. On this you may get LAQ also. So see, the rate of loss of heat is directly proportional to the temperature difference between the body and its surrounding. The rate of loss of heat is directly proportional to the temperature difference between the body and its surrounding. See here, minus dq by dt, this is what rate of loss of heat is directly proportional to temperature difference. This theta naught is what? Surrounding temperature. Now, if I am removing this proportionality sign, I am adding one proportionality constant. Minus dq by dt is equal to C into theta minus theta naught. And This law holds good for small temperature difference about 30 degrees Celsius only. Okay. So note down this. We will see some applications of this. First note down. See this application. Just now we have seen minus dq by dt is equal to c into theta minus theta naught. Now at the place of this dq, I am substituting ms d theta. You know this, q is equal to ms delta theta. Same thing I have substituted. Minus sign indicates rate of loss. So let's transfer this ms this side. So minus and ms I have transferred here. So c by ms you are getting here. Just this ms I have transferred here. So d theta by dt is equal to minus c by ms into the theta minus theta naught. Now let's assume that this minus c by ms is k. Okay. And then we are getting d theta by dt is equal to k into theta minus theta naught, where this k is called cooling constant. K is called cooling constant. Okay. Now if body cools from uniformly from theta 1 to theta 2 in time t, then theta is equal to theta average, and that is equal to theta 1 plus theta 2 by 2. So at this theta, you substitute theta 1 plus theta 2 by 2 in this case. Then d theta by dt will become theta 1 minus theta 2 by t, because this is change in temperature. So as temperature changing from theta 1 to theta 2, you just substitute theta 1 minus theta 2 by t. And then this equation becomes like this: theta 1 minus theta 2 by t is equal to k into theta 1 plus theta 2 by 2 minus surrounding temperature, and this unit of k is second inverse. Okay, so note down. So let's see some cooling curves. First curve I have drawn, that is log of theta minus theta naught versus time, and it is like this. So how we are getting like this? See, we have seen d theta by dt is proportional to minus theta naught, and if we will transfer this theta naught here after adding the proportionality constant, d theta by dt is equal to minus k theta minus theta naught. So I am transferring this theta minus theta naught here and dt this side. Okay, so what we are getting, log to the base c theta minus theta naught, because this is, we have to treat as a 1 by x, so integration is log x is equal to minus kt plus c. So next we want to find the c value, that is constant of integration. At t is equal to 0, let theta is equal to theta 1, and then if we will substitute here t is equal to 0, we are getting c is equal to log e theta 1 minus theta naught. Let's substitute that value in this equation. So log e theta minus theta naught is equal to minus kt as it is. At the place of this c, I am substituting this value, log to the base e theta 1 minus theta naught. Next cooling curve, that is theta versus temperature, and here again same equation I am taking, which we have seen here. So log e theta minus theta naught minus kt log plus log e theta 1 minus theta naught, which we have seen here. Now let us assume that a is equal to theta 1 minus theta naught. So here we will substitute that. So we are getting log e theta minus theta naught is equal to minus kt plus log to the base e a. Just we have replaced this theta 1 minus theta naught as a, and then you transfer here log e theta minus theta naught minus log e a, so log a by b, and that's why log e theta minus theta naught by a, which is equal to minus kt. So take exponential, what you will get, theta minus theta naught is equal to a e power minus kt, and that's why you are getting this exponential curve. Okay, you can draw this and note down. So next curve, that is rate of cooling versus temperature. You can see here R is rate of cooling and temperature. If we will plot the graph, we will get like this, which cuts negative y-axis. Rate of cooling is R, which is equal to minus d theta by dt. That is what rate of cooling. So minus d theta by dt is equal to k into theta minus theta naught. We know this. Now I'm just replacing with R, then k theta minus k theta naught, and that's what this graph suggests you. That is R is equal to k theta minus k theta naught, and that's why you are getting like this line, and this part which is here is nothing but k into theta naught. Theta naught is surrounding temperature. Okay, and this is the end of this chapter. Okay, watch it and write the notes. Bye.